what is the final steam quality? Okay, quality. So for the quality, what I need to do is relate the properties that I know, right? I know the quality is going to be the specific volume that I have, so 2 minus specific volume for the gas divided by the difference, the specific volume for the, the fluid. Gas minus specific volume from the fluid, okay? And we have all these values from the table. This is simply going to be the 0.6057 that we calculated minus the table value of 0.001043 divided by the gas one, which is 1.694 minus 0.001043. Okay, and the quality then is 35, approximately 35.72%, and that is our answer. So there's 35% steam and 65% approximately liquid. Okay, that's the mixture that we have on state number 2. So quality is 35.72%. Last but not least, what is the heat transferred? Okay, how are we able to get how much heat is transferred? Well, if I'm able to define the full states, and I know that there was no change in volume whatsoever, right? We always know that. So we can apply our first law, right? We're talking about a closed system. The closed law, first law for closed system says that is heat plus or minus work depending on where you are at. So this means that if I have no work, and I have no work because my volume did not change, then the difference in internal energy can tell me about my heat. So all I need to do to find the heat is get the final state minus the initial state and do the math there. So that's super simple, right? I just need to go back to my table. And let's just use this one because we've been using this one for the last values. Okay, and here we are. We are at, for the first state, we are at 300 and it's saturated. So all we need to do is internal energy, saturated vapor, and grab the value here, so 2543, right off the bat, okay? And then over here, what I need to do is, okay, because it's a mixture, I need to get 35% of this guy here, and then the 65% of this guy here, the 417, okay? That's how we go about doing that. And we have it all, we have that, 25, okay, so that's all, you only need to do the math. What would you do on this table here? It's the same deal, it's the same thing, nothing changes. Internal energy for the gas, internal energy for the fluid. Okay, so we're going to do 35% of this guy here and 65% of this guy here. Okay, and then for the first state, it's a saturated vapor, so we can go ahead and grab 2544. Which table to use? Again, it depends on your professor, it depends on who you're working with, what they ask you to do. I'm going to go ahead and grab the values that we've just discussed, and I'll do the other table just to make it simple on me. So where's our math? Here you go. Okay, so let's start with U1 because that's right off the bat. We got it just 2544, and that is kilojoules per kilograms. And then U2 is a mixture, so therefore I need to do, okay, this is going to be the internal energy for the liquid times the however much liquid I have, so it's 1 minus the 0.3572 plus the 2 what was it, 2, I forget, sorry about that, 1 bar 2506 506 times the 0.3572. What's the other way of calculating? Well, it's using the difference, right? Because this mathematically is the same as just using the difference and considering just the liquid one. So how would that look like? It will be the 417 from the liquid, plus the amount of vapor, so 0.3572, times the difference. And the difference is this minus this, and this is also on the table, so that's why it's there, so we can simplify your life. It's 2088.2, and then if you do this math, both it should be the same, obviously, but I got 1,163.93 kilojoules per kilograms. All right, now we have these two values. We have this guy. We just need the difference, right? What you note is that Q2 is actually greater. So that just, smaller. So that just confirms what we suspected from the beginning, right? That actually heat is not entering the system, rather it is leaving the system. So 2544. So therefore Q equals 1,380.1 kilojoules per kilograms. All right, so you can write it like that, or you can say heat leaves or heat out, and then you don't need the negative, and you can say it like so. Both are correct, both are your answers, both should be accepted. Okay, I hope this was useful. If you have any questions, as per usual, just leave them down below in the comment section. If this was helpful, consider giving it a like. And to finish this off, the last thing you can do if you want, and depending on, again, on the way your class is structured, is to multiply this result here by the mass, because sometimes you're able to grab the mass. And the easiest way to know is if they're giving you the volume or not. Okay, and here's obviously another indication, which is your answer is not in kilojoules per kilogram, but rather in kilojoules. So whenever you're given the mass, there's a very strong chance they want you to calculate the final answer without the specificity of the mass. How do we go about that? Well, the mass does not change. You can grab the state 1 or state 2 because it's going to be the same, and we know that specific volume is this. Right? So all we need to do is relate this back to its fundamentals. Specific volume is meters cubed per kilogram. Therefore, this is volume by mass. And therefore, if I want the mass, all I need to do is take the specific volume, take the volume and divide by the specific volume. So in other words, you just need to take the 0.5 meters cubed, divide that by 0.6057 meters cubed per kilogram, which allows me to get the amount of mass that I have, which is 0.8. So 0.8255 kilograms. Okay, and then with this, I can multiply my heat here